And our next speaker is Enrico from the higher order company, who is here to tell us about what I think can easily be called a radical new suggestion for how we should compute functional programs. Well, yeah.
One moment. Hopefully you guys can see that okay. Let me make sure I can move around. Yes. So yes, my name is Enrico Borba. I'm here with the higher order company. We're going to be talking about interaction combinators, our runtime for evaluating them. And this is a joint work between a lot of people. Me and Nicolas, we're here at the conference today to talk about this. So the main ideas that we want to bring this around. The main things we want to talk about today are an efficient interaction combinator runtime. The reason that matters is we can encode the computational models that we're typically familiar with, like Lambda calculus, inside of interaction combinators. Additionally, our design for this runtime is mostly hardware agnostic, and so we're actually able to port these ideas to both the CPU and the GPU. And because it's so abstract, there's an opportunity for compiling higher level languages from a variety of domains into these interaction combinators. So since it's such a non-traditional model of computation, I'm going to be giving a brief introduction on interaction combinators. The general idea here is a graph rewrite system. And if you can imagine, we'd have a graph that's sort of the initial state of the program. According to some rewrite rules, we're going to change the graph over time, eventually ending up with a graph where no more rewrite rules can be applied. And hopefully by the end of this talk, it'll become clear that the graph here on the left represents a lambda calculus term that's applying the identity function to itself, which you would expect in sort of a sane evaluation environment. You should get back the identity function again. Yes. So the specific system that I'm going to be introducing today and then extending on later in the talk was developed by Mazza and Lafont, sort of work building up on top of each other. So the general building block for these graphs starts with some nodes, like the typical graphs that you're probably familiar with. However, these nodes have sort of special edges that come out of them, known as their principal ports. And the binary nodes additionally have two auxiliary ports that come out of them. While we're talking about these, typically the way we choose to refer to them and how they've also been seen in the literature is the white node is the constructor, the black node is the duplicator, and then we have an eraser node as well. And you'll notice the eraser only has a principal port and no auxiliary ports coming out of it. So that's the first step of the graph, and you can imagine those nodes are all wired up together. The sort of second part of the system is the rewrite rules that govern how the graph should change over time. And depending on how you count, there's 4 or 2 rules. They're sort of generalizations of 2 basic rules. So we have here on the top, these rules are known as commutation. If you have 2 nodes that are different types interacting with each other, they will commute. And what that sort of looks like, if you can imagine, one node will go through the other along its auxiliary ports. So here we have the constructor node interacting with a duplicator node, and you'll see that the duplicator node moves down the 2 auxiliary ports of the constructor node. Similarly, the constructor node will move up on these 2 ports up here. And whatever these 2 ports are sort of connected to in the rest of the graph, it's meant to still be connected to after the rewrite rule is applied. Like I mentioned when I was first introducing this rule, this happens when 2 different types of nodes interact. So you can extend this to erasers, which are these nullary nodes, and binary nodes. And sort of, since the eraser has no auxiliary ports, there's nowhere for the binary node to go, but the eraser will move up into the auxiliary ports of the binary node. So that's commutation. The second rewrite rule is annihilation when 2 nodes of the same type interact. So you can imagine this rule also being instantiated for the duplicator nodes. And what happens is the auxiliary ports cross over. In a degenerate case where 2 eraser nodes interacting, that sort of part of the graph disappears. You'll see that that's meant to represent computation of sort of variables that are thrown out. If you imagine a lambda term that takes in 2 parameters but only uses 1, and the other one sort of gets thrown away, that's typically how erased computation ends up being represented in these graphs. Additionally, you'll notice that this rewrite system is symmetric. It's sort of up to the labeling of the nodes. If one of them is being black, one of them is being white, they're identical in behavior and how they change the graph as it's rewritten over time. Does that make sense? Any questions so far? Cool. Now, I've given us sort of some nodes. I've given us the rewrite rules. How do we do the typical lambda calculus computation over these strange objects? So what we want to do is we want to take existing lambda calculus terms and transform them into these graphs. And in the lambda calculus, there's the 2 typical operations that we're familiar with, where we abstract a variable inside of a body, and we can also apply a lambda calculus function to a variable. Perhaps less known operation, at least it doesn't really matter when you're writing these lambda calculus terms, is duplication. This occurs when you have to use a variable more than once. If you think about sort of a variable existing in this graph representation as a wire, you can't use it more than once. That wire only has to connect to one place. And so duplication is the way in which you can reuse terms. So let's go through these one by one, because it's kind of a strange way to compute. Abstraction, the way to think about this is this left wire here is going to be the variable that you're going to use in the body of the lambda function. The body of the lambda function is the y, and the term is what comes out of the principal port at the top. So if you want to make use of this lambda term, that's an abstraction, you would connect this principal port elsewhere in the graph where you want to use it. A very simple case is the identity function. So when you take in the parameter you're abstracting and just use it in the body and nothing else, that would just be connecting the input parameter to the body. And then you would use that identity function by connecting the principal port elsewhere. Now, for abstraction, the sort of output of this syntactic construct comes out of the principal port. For application, it's slightly different. When you apply a lambda calculus term, you need a function and a parameter. And so those will come in at the top and at the left auxiliary port respectively. And the result of that application actually comes out of one of the auxiliary ports. The reason for this sort of encoding you'll see in a moment is, like I mentioned at the beginning, or early in the talk, the way we have these nodes interact with each other or be rewritten is only when they're connected through their principal ports. And abstraction and application are only, basically when you need to do a beta reduction in lambda calculus, it's when an abstraction meets an application. And because the applications take in the function through the principal port and the abstractions output their functions through the principal port, when you go to abstract or apply an abstraction, the rewrite will occur through the principal ports. And I'll go through a more detailed example of these constructions in a moment. Duplication, like I mentioned earlier, if you ever need to use a variable more than once, you can duplicate it. The principal port is where the variable comes in, and these two auxiliary ports are now how you can use that variable more than once. Please go ahead.
So how do I know if I see a triangle with these three,
Yes.
whether it's an abstraction or an application?
That's a fantastic question. In general, if you construct a random network, you can't necessarily read it back as a lambda calculus term. However, when you're constructing it, the rules are pretty sort of explicit. Intermediate networks, as the graph is being rewritten, can't necessarily be read back or interpreted as a lambda calculus term. Does that make sense?
In the standard literature, abstraction and application are different nodes.
Sorry?
In the interaction nets literature, abstraction and application are different nodes.
It depends on what you mean by different nodes. Some literature has them as the same nodes. However, they have a property known as polarity, where this wire is positive and these two are negative because they're sort of consuming values and this is outputting one. And this one here has a positive wire and two negative wires. If you want to walk a network and infer the polarity, you can sort of see them as different nodes. However, this is a fine way to encode lambda calculus terms.
In interaction combinators, we represent both of them with the same node. And if you can imagine, you could polarize the system. And the difference between an abstraction and an application is that they have two different polarizations, and the polarizations are consistent under data reduction.
You do have readback, right?
Yes.
But not intermediate readback. You can't read back like an intermediate network necessarily.
Okay.
Yes.
Could you give an example where,
Yeah, the next slide will give an example. Yes. And the last construct, just before I go to the next slide, is just erasure. Like I mentioned earlier, if you don't use a variable, you can't have these open ports sort of not connected to things. And so this is a way you throw away a piece of computation. So here's an example reduction going from the left to the right. We're going to start off with the same term that I showed in the beginning of the slides, where we're going to apply a function that takes in a parameter and applies it to itself, to the identity function. So I've colored the active pairs of the reducible expressions in red, and additionally, they're sort of drawn in a way that's meant to make reading this a bit easier. This left-hand side of the first step is this term here. So this is an abstraction with a duplication, and then an application of the x to itself. And the result of that is the body of this lambda expression. So again, this is an abstraction with one parameter that is duplicated, applied to itself, and the result of that application is this term. The identity function, like I mentioned earlier, is down here. And this extra construct is to apply the first term to the second. So this is an application of this function to this term. This R here is the port that we're holding on to essentially to keep the computation. We need a free port. You can think of this as like a combinator in lambda calculus, but if there are no free ports, essentially the computation can result in like a void net. And so holding onto this free port gives us a result value to refer to later on.
But since that R seems to be like the output of the application of the first lambda to the second,
Mm-hmm.
would it be fair to say that that is the result of the whole?
Yes.
Okay.
Yes. So the first rewrite rule, or the first reducible expression that we reduce is this red active pair here. That's going to be an annihilation because two nodes are the exact same. And these wires cross over. And you're going to be left with this R is going to end up down here. And this node is going to connect to this node through the active pair, which is what I've represented up here. And I've drawn it just to save some space where the identity function came up to the top here. This net, I don't think, is interpretable if you wanted to read this back to give you an example of a network that intermediately doesn't make much sense as a lambda calculus term. Which I'll show later in the talk, we have the syntax to describe these, but they're not lambda calculus terms. Yeah, so the second rule we apply here is a commutation rule. As you can see, these two nodes are different. And so this node and this node will commute. Hopefully that is somewhat clear here. You can see the duplicator node moved up into the auxiliary ports of the constructor node, and the constructor node moved down into the auxiliary ports of the duplicator node. And then we have one annihilation of the two duplicator nodes. Yes, that's right. This port here goes through and connects to this one. This port here goes through and connects to itself. So this node came down here, and this node became that one. And there's one more active pair to reduce, and again, that's another annihilation. This port here ends up just going through and connecting back to the principal port of this function, or of this constructor node, excuse me. And as we expected, that is the same representation for an identity function, which is what we expect if we were to reduce this expression. That is a so if, okay, there's a few things to this question. If the network you have represents a valid lambda calculus term, you can read it back by inferring the polarity of the nodes. Because you know the polarity of the output, and so you can basically walk, and there's a fixed, there's constraints on the positive, like if you think of these nodes as being directed, or excuse me, if you think of these edges being directed, you can infer the direction of every edge in a network. But that's only, again, assuming you have a term that's a valid representation of some lambda calculus term. If you have a network that represents a valid lambda calculus term, you can infer this polarity. So both in the start and in the end case, we can infer that. In the intermediate cases, we can't. Now, I think perhaps this will answer your question. This does not soundly reduce the entire lambda calculus. All right, so this reduces a subset of the lambda calculus. Specifically, you can't duplicate a function that is non-affine, because that would end up resulting in two duplicator nodes interacting with each other, which would result in a destructive computation, which really isn't what should happen. A function that uses every parameter at most once. Does that make sense? So a linear function would be one that uses their parameters exactly once. Affine uses at less than or equal to once. Correct. It's a function with no duplication nodes, or a lambda term with no duplication nodes. That is not trivial to infer. It's not clear, just given a lambda calculus expression, if you will end up duplicating a non-affine function.
Well, the first, then in that case.
This is not affine?
This is already not affine, but this is worse. Yeah, but this is
No, but you're not duplicating a non-affine function.
It's duplicating a non-affine function.
Yes, it's a strange constraint. But essentially, you want to say that you don't have two duplicator nodes interacting with each other.
Basically, the problem is if a duplication duplicates another duplication.
Yeah,
Right?
yeah, exactly.
Then you get an annihilation when actually the behavior that you wanted was the commutation.
But that's not a modular property, right? I can't, like, for the whole program you can say that or not, but it doesn't mean that I can't write functions and type check and check them one by one. And it's only when I have the whole program I will find out that I can't compile it to an interaction.
Well, so you can't compile to this presentation of interaction combinators. You can imagine one where for every function you create, you actually create a new type of node. Like every function has its own duplicator node, its own special label. And so whenever two duplicator nodes meet, they'll never be the same label. They'll always be different. At least when applying functions that are different. But yes, correct. In this system, there are like this reduces soundly only a subset of the lambda calculus. Any other questions on this reduction? Yes, please.
Figuring out if a function is affine, is that like a resident analysis? I think you were saying it's floating, right?
Affinity is checkable, yes.
So you have to look at the whole program?
No. You can check if a function is affine.
Yeah, okay, so like the identity function then is, the other one isn't.
Correct. That's a syntactic check. But to ensure that I think that a whole program never duplicates a non-affine function, it requires the entire program. Okay, some quick important theory that we're going to make use of that the HVM depends on. There's two important points here. Interaction nets have a very interesting property such that the actual order in which you apply the reducible expressions is irrelevant. The number of reducible expressions, or the number of reducible expressions that you will end up reducing as you're evaluating a network is always the same, independent of the order of which you decide to take those operations. And that ends up being extremely useful for a parallel evaluator because you can sort of, it doesn't matter, as soon as you see a reducible expression, you can go and evaluate that. And you won't sort of get penalized for happening to pick some specific order. Additionally, the nets that we care about are these networks that have a single free port and have no vicious circles. Vicious circles are essentially a network whose wire eventually, like if you can imagine a tree of nodes, if a wire ends up connecting back to its principal port, that is a vicious circle. It represents a computation that at least we're not interested in. It's not in the surjection when encoding the lambda calculus terms, and it'll never be an intermediate net either. Please. So, yeah. The Wikipedia page entry for strong confluence, I think, agrees with what you're saying. In the Lafont 1997 paper, the way he defines strong confluence is the fact that if at any point we have some network, here N0, and you can do one of two reductions. You can go to N1 or N2 as a result of applying either reduction A or reduction B. There is always, for each of N1 and N2, you can always take another step to go exactly to an equivalent third state. So if you ever have the choice between two reducible expressions to reduce, if you can pick one or pick the other, it says that among those two choices, I can always return to a third shared state. Does that make sense what I'm saying? Perhaps I'm not explaining it well.
Yeah, but I'm not sure that those arrows, correspond to,
Yes. What I'm saying is, in the Lafont paper, his definition of strong confluence is that these arrows are single steps.
Is it the case that you get the property because the evaluation is optimal regardless of the path you're taking?
The property that the amount of work is independent is due to this definition of strong confluence, which I agree with you disagrees with like the Wikipedia page entry, but the way when Lafont is like presenting this, the way he states strong confluence, which I don't have a, perhaps I should call it stronger.
Definition of strong confluence, yes.
But
his contention is with the amount of work claimed.
The amount of work being dependent is it derives from the property of
strong confluence.
Yes, and the fact that each path is optimal, right? Yes. So that's the missing bit, right?
Because if this is the terminal state,
Because, like for instance, you have an erasing node, right? So you have an interaction, you have a choice of interaction node. Do you want to duplicate first, or do you want to sort of, get the erasing node to sort of eat up eat up as much as you can. So if you sort of duplicate and just keep duplicating, then there's a lot more work for the erasing node to
but that duplication would have happened regardless.
Yes, but the thing is that you see, then the amount of work is different. If you let the erasing node optimize on erasing first, then there will be less work.
No, I think the amount of, so independent of the order, the number of interactions that occur is constant, always. At a minimum, we have empirical evidence of this, but it's also like a theoretical result. And one of the effects of choosing which reductions to happen, or I guess one of the penalties of perhaps taking some order of reductions versus another is the amount of intermediate memory. You're correct if you go and do all of the commutation rules first, your intermediate network is going to be much larger than it would otherwise be if you did all the annihilations first. However, the number of interactions is constant. And again, it's due to this property.
maybe there is a confusion that in here in this system we are always executing every single interaction that exists. Right? So, for example, if you want lazy evaluation, then you don't need to do the interactions that are not actually important, like that are disconnected from the value that we want to execute. And then under lazy evaluation, then yes,
That is true. If some part of the net ends up being disconnected from the main network and essentially won't affect the end result, it's still reduced all the way. And that's included in my count of like the total number of interactions.
This is essentially the same trick that CDD does.
Sorry?
On a CDD system, like all the parts of the program are going to be reduced. So the total amount of reductions is always the same.
Yes. But you might do some reductions that you perhaps wouldn't need to if you were doing an optimal evaluation because of these part of the networks that were disconnected.
But so with the translation, if you start from a left term and then you do the interaction, that reduction, and then you read back. But if you want to do lazy evaluation, like how is it easy to
Yeah.
tell when you can read back the amount that corresponds exactly to the lazy evaluation?
That's a good question, and that gets into sort of the extensions that HVM2 does and the sort of how it builds upon the symmetric interaction combinators. And so I'm going to go through the implementation details of HVM2. First thing is the fact that we need like a textual representation for these networks, both as a way to sort of reason about them, or at least to have a computer reason about them, and to have them be a compilation target. The idea behind the textual representation is that we want to represent parts of the network as trees, and I feel like I'm going to have a hard time explaining this, but there's different kinds of nodes, and these binary nodes have two different ports, and the way we represent that textually is we have different grouping operators, or different symbols of grouping to represent the different kinds of nodes, and there's two different terms you can put in these binary nodes, whatever the left auxiliary port is connected to and whatever the right auxiliary port is connected to. We also have a concept of variables, which means we have to label the wires. This is a key difference between the graphical representation. The graphical representation has no labeling of these wires, but we're sort of forced to do that in order to encode this textually. Essentially, variables, as they're encountered from left to right, they are matched up as wires. Variables have to occur exactly twice because a wire needs to connect from one thing to another. So these two examples here are two examples of simple binary nodes where the auxiliary ports are connected to themselves, or connected to the same node's auxiliary port. Here's a more complex one where we have a constructor node, a duplicator node on the left. So you can see there's a duplicator node on the left. And then on the right of that duplicator node's auxiliary port is another constructor. And you can see the wires, if you just match up the x's and the y's, they connect as they're shown in the graphical representation. The additional syntactic construct we need is to connect these trees through active pairs. The way this is done is a collection of active pairs, and so you have some main tree, in this case it's just a wire, so a degenerate tree, and a collection of active pairs. Perhaps I should have written the BNF grammar here, but essentially you have an ampersand symbol, a term, tilde term, and then perhaps an optional ampersand symbol with more term tilde terms. You have a collection of active pairs and the main tree that is going to be the port, the free port of the network. So here, this could be any variable. I'm just picking R. R is going to be the free port in the net. And we have one active pair here. On the right-hand side, we have a constructor node with two erasers connected to the R that ends up being the free port of the network. On the left-hand side, we have this other term that I've shown here. Does this make sense as a textual representation? It's very, perhaps, unintuitive, but go ahead.
Ampersand and tilde are the same operator.
Correct. It's ampersand term, tilde term, ampersand term, tilde term. If you wanted to add another active pair, we would do ampersand and then some tree interacting with some other tree. Cool.
So sorry, what's the role of the thing before the ampersand?
Yes, so the networks that we're concerned with, and they take this shape in general, which is some free port connected to a tree, and then a collection of active pairs, and they're wired up in some way, right? And so every network that you're going to be able to assign to an identifier in HVM syntax has a free port, because that's what you're going to use to, if you apply that identifier to another one, if you, essentially like, if you imagine, exactly, you need a way to interface with other networks and to compose them. And so you need this free port.
But that also means that like, of course, that thing can only be connected, only one end of this can be connected internally. So
Yes.
like it's somewhat redundant because you could figure out that what is the one variable that, or one wire that only needs.
Yes.
Okay, then it makes sense. Okay, thank you.
The reason we want the free ports, though, is because we're going to assign them to identifiers, which is another extension we have. You can name the networks. One of the key points of being able to name your networks with identifiers is the fact that this introduces laziness. You can have a self-referential network, which is not representable in like the vanilla interaction nets because you basically have an infinite network. As Nicolas mentioned, the environment we're working with here is complete like strict evaluation. Any active pair that exists will be reduced. It doesn't matter if it's connected to the main program or not. And so this allows you to introduce laziness. It's essentially deferred computation. Until this reference is interacted with, it will not be evaluated. So
can we understand the ampersand as a binder? Like it's binding the variable R?
no, the ampersand is just prefacing a reducible expression. So yeah.
You can have an array of things that you can execute, right? And the ampersand is like adding a new entry to this array of executables.
It's kind of like a comma. Yeah.
Okay.
If you have variables on the left-hand side of the ampersand, or let's say like, for example, the R wasn't referenced on this right-hand side here, that would be sort of a net with two disconnected components, which doesn't make much sense. And so the idea is you're going to end up connecting the different parts of the network through these variables.
I'd like to ask,
Please.
understand the curly brace. So, and the little jump,
Sorry?
ordinary lambda calculus notation to something where,
Yes.
so ID is lambda x dot x.
No. ID is, this is all HVM syntax. So this is a constructor node with its auxiliary ports connected to itself, which is what's represented up there. Unfortunately, it also, if you were to write like a lambda calculus syntax, this looks like.
Yeah, you see, sort of just the identification.
You translated it, and now we are doing graphs. We don't care about lambda anymore. We're not. This is a graph. Like forget about lambda. Right? Like this is
So,
now.
it's just a graph. So, I mean, how am I supposed to make sense of? I mean, I can't use any of my lambda calculus intuition to evaluate this.
Yeah. That is an unfortunate I mean, we're faced with a task of being able to textually represent a graph that can have wires connecting very distant portions, right? And so we need these variables to connect those distant portions. Unfortunately, if the variables are very close to each other, yes, this also looks like a lambda calculus term. But what I hope is somewhat clear is the grouping operators form a node, and they have two arguments, which is the left port and the right port. And the variables, the names themselves, just like in a lambda abstraction, don't really matter except with the other variable it's paired with. So this x is just saying as soon as you see another x, connect the wire together. And so it represents that node up there, which has two auxiliary ports that they're connected to each other. This iter reference here is that term over there, which again is a constructor node with a duplicator node on the left auxiliary port and a constructor node on the right auxiliary port of that duplicator node. And this term here perhaps is the most confusing among the already confusing terms. Essentially what it's saying is the main network is identified by some free port, which we're going to give a name, and a collection of active pairs. The active pairs are going to be this constructor node, which is this one here, whose left auxiliary port is connected to a reference, whose right auxiliary port is connected to R, which is this variable here. So again, this is the free port of the reference. And it's interacting with a reference node. And so that's why this is connected to the principal port here. Okay, any questions? So this is the first extension of the interaction combinators where we have references. The second extension is, yeah, no, go ahead.
Because you just said something that basically, so you said you said references. So when you write, like it's not graphing
It's a new kind of node. So previously when I introduced these, we had three kinds of nodes. We had two binary nodes, the constructor and the duplicator, and we had an eraser. This is a new node with no auxiliary ports. And it's a node that...
Not just grafting.
Yes.
It's not like I don't know what the right word would be. It's not macrosemantics, basically.
No, it's a new node in the interaction nets, exactly. And it's a node with no auxiliary ports.
Okay.
And so we now, in some sense, have like a family of nodes because references that have different names are different kinds of nodes.
So when this reference node interacts with something else, the result is that you copy this reference net. So you can have like this collapsed view of the network as a reference, and then it's only expanded when you actually interact with something.
And the copy is not atomic, right? It's like an actual deep copy.
Yeah.
So in the text representation, if I wrote like at main, it would replace where I put at main with the 3-port R.
Only if it's interacted with. Only if it ends up being on like the left-hand side or the right-hand side of a reducible expression are they expanded.
Sorry. I have a question about the variables. So the semantics here is that the variables on like, let's say at ID, it mentions X, and at inter, it also mentions X. Those are completely unrelated.
Yeah.
It's essentially alpha or
Yeah.
or something like that.
So variables are first scoped to references, and so you can't have like one variable in one reference refer to a variable in another reference. That's already not possible. And they're paired up just reading left to right. So when you see an X, the next time you see an X, we're gonna increment some variable counter, and that's like variable 1. If we see, go ahead.
Essentially there is a binder, like the reference itself binds all the variables.
Yes, but yeah, but if you see X like 4 times, then it's just the first 2 X's are paired, the second 2 X's are paired. Cool. So this is the first extension. Again, we're adding a new family of nodes, which are reference nodes, and we're adding some rules, which Nicolas alluded to, which is if you ever interact with a reference node, you do a complete copy of what that reference refers to. This extension adds like numeric primitives, and this is, as it perhaps is obvious here, the most complicated extension. The actual details, I mean, they're detailed in the paper if you want to see them. The intent here is to be able to have a node that represents a number, and additionally be able to do operations on those numbers, like the operations we're familiar with, like addition, division, multiplication, etc. There's a few immediate problems with this. One, our ports, or our nodes have 3 ports, right? There's a principal port and 2 auxiliary ports, and so you have to store the operation somewhere. And you have to additionally have the result of the computation exit somewhere. So there's a few immediate, perhaps, options, right? You could have 1 node per operation. You could have a multiplication node, a division node, etc. Unfortunately, because of the constraints of the environment we're working with, which I'll explain a little bit later, we have exhausted all of the space we have to represent nodes. And so we cannot store, at least not in a binary node, we cannot store additional information. So the route that we have gone with, which is kind of nuts, is the numbers themselves will store the operation. The numbers are typed, and so you can imagine a 24-bit, or like you can imagine some like bit string of numbers where 3 bits are reserved for a tag, so a 32-bit number, a 29-bit value, and the low 3 bits are reserved for essentially describing if it's an int, a float, or unsigned. We can also use those bits to store operations. And so essentially what ends up happening is numbers end up storing, they end up becoming partially applied, right? When a number encounters an operation, it replaces its type with that operation, and now you have essentially this untyped number that's like partially divided, and when it encounters another number, it'll encounter a typed number, and you'll know what the type of both numbers should be, what operation it should be, and what the result should be.
And this can go in both directions, like you can have a left partial application to the right partial?
Yeah, we have rules which are not displayed up here, which again are in the paper, that order, like we'll swap the order of the numbers if you have the operating number on one side when it really should be on the other. But yes, one number will carry the operation, the other will carry the type. And additionally, what we wanted to add as well is case matching. We wanted to add like conditional execution. If a number is 0, sort of reduced to one thing. If a number is something else, reduced to another thing. This essentially captures that. The structure of this reduction perhaps does not seem obvious or like doesn't make any sense really. It's quite convoluted, but the idea essentially is that X is going to carry a pair or a tuple where if n is 0, we're going to erase one side of X. If n is greater than 0, we're going to erase another side of X. That's the intuition behind this reduction. The details aren't that important, but the idea, again, is that we're able to represent numbers in a primitive way.
So this breaks from frequency, doesn't it?
Sorry?
This breaks from frequency, doesn't it?
No.
It does if you pass something that is not a number.
Okay.
And then we,
Sure.
by construction of our programs, we ensure that they are like type correct, and then the properties of your system remain. But these are not like actual interaction net rules.
Okay, I see. Yeah, no, sorry. But the thing is, you're erasing one side of it.
Say it again?
You're erasing one side of it, right?
We're erasing one side of X in one branch and another side of X in another branch.
But you're still computing that side that you're erasing.
If it has any active pairs, it will be reduced, yes.
Okay.
Yeah. Again, you can refer to the paper for this exact same diagram. This is just the encoding of the interaction net rules with our extensions, but on top of the textual syntax. So these are like the interaction net rules, instead of written graphically, they're written as a rewrite system on top of the textual syntax. Okay, so this will go to, this is sort of what I was alluding to earlier about the memory constraints of our, the design of our evaluator. I guess before I go into the details, I'll preface this with the fact that like the limiting factor, one of the limiting factors is the fact that we need 64-bit atomics to do certain operations, essentially to ensure that that there's no like thread contention, because the reducible expressions are stored as 64-bit values, and when you want a thread to work on a reducible expression, you want that thread to atomically grab it. The memory layout that the HVM2 uses is we have a list of nodes and a list of reducible expressions. The nodes themselves don't know what their type is. They just know what their auxiliary ports are connected to. A node's type really only matters anyways when it's going to be as part of a reducible expression, and you can see in the reducible expressions here, they contain the type of the nodes. So this memory layout is meant to represent this interaction net here. We don't have to go through all of it in detail, but you can see here in the red X bag, we have a constructor node at index 2. What this essentially is saying is that this red X is interacting two constructor nodes, the second and the third one. So these two nodes are interacting, and you can see BA is interacting with XY eraser, and that is what's represented down there. Some other consequences, since the ports are storing the types of nodes, they need a tag. We have 8 nodes, and so 3-bit tag. That means that they have a 29-bit value, which means that since ports store the sort of address of the node, that gives us a 29-bit address space, which is 4 gigabytes worth. And so if you have a GPU with a lot of space, we can't utilize all of it, which is unfortunate. Ports, additionally, for nilary nodes, nodes that have no auxiliary ports, they store the node like in line. For example, here, the node, this is a reference node to the first reference, which is the only one in the program, which is foo, for example. Yeah, this is the memory layout that we have gone with. This is 2 components of the memory layout, at least. The main sort of contribution and insight of this that allows us to scale the evaluator onto a GPU, which runs like 16,000 threads, is the fact that the linker is lock-free. Let me back up real quick. One interaction we have, which is not at all present in the graphical representation, is essentially like substituting variables, right? You have these variables in the graph, and if you go and interact with a variable, you need to sort of see or replace that occurrence of that variable with the actual term that it's connected to. And so we need a mechanism for essentially if you have two reducible expressions that are making use of some variable, eventually we need this node to interact with this node here. The way essentially this works is an atomic map. The first time the variable is encountered, it's inserted into the map. And since we know the variables occur only twice, the next time that variable is seen, it will be retrieved from the map. And now that second thread that had access to the variable will have access to both of the nodes and will appropriately push that reducible expression to the stack of reducible expressions that's getting worked on by the other threads. Again, because this extraordinarily heavily relies on the fact that, or whatever the maximum width atomic integer support the platform has, that is what allows us to sort of have nodes of different sizes. The reason we chose 64 bits, like I mentioned, is not all GPUs have 128-bit atomics. Not all GPUs have 64-bit atomics either. But that felt like a good enough compromise given the fact that we'd have to give up a lot of addressing space already to go just on 64-bit nodes. Yeah, go ahead.
Do you ever get the scenario where one node encounters the first current spec, and then one thread encounters the first current spec, and then the second one encounters the second? Like, how do you stop that from causing problems? Because do you need to?
Sure. So because the map that's sort of holding the variable substitutions is a map of atomic integers, one thread will insert the node into the substitution map first. Variables are just indexes into an array. And so some thread will insert this node essentially into, if R is the fifth variable, it'll insert this node into the fifth position of the array. This second thread will go and do a swap. It'll insert this, this node into the substitution map. If it receives something, essentially, if what it got, this is pseudocode, of course, but if it receives something back from the map that was already, that means something was already there, some previous thread had already inserted it, then the current thread actually has ownership over both nodes, and it can go and take it back out and interact both of those nodes. Does that make sense? The second thread, if it attempts to insert another node and it sees that it didn't get a 0 value back, it knows that it has ownership over both of them, and it can go and retrieve that node it just inserted and push that redex into the stack. Yeah, so as I've been mentioning, right, the atomic operation support limits the addressing space. 64-bit atomics imply 64-bit address space. The memory just isn't fully utilized. One additional sort of trick you can do to limit the amount of memory usage is the fact that annihilation deletes two nodes, so you reclaim memory, and commutation creates two nodes. And you can use that both to your advantage to share work and to reduce memory pressure, right? If you're running into memory limits, you should probably do as many annihilations as you can. When you're spinning up the interaction, though, you probably want to do as many commutations as you can so the threads can have work to do, because you know that work is going to be done anyways at some point. Yeah, this is essentially what I was saying earlier. The GPU is especially difficult to schedule work for. You have all these threads that want to go and operate on things, and ideally the threads are all taking the exact same execution paths. And so we have, specifically for the GPU, a mode for the runtime that does, it prioritizes commutations to grow essentially the bag of redexes. It'll switch to a work mode once it feels that the number of redexes has grown sufficiently. Additionally, because of the sort of hardware structure of a GPU, threads are in blocks that can share memory. And so threads will share memory with the block of threads that they're a part of. However, you really want to share work sort of globally. And so periodically, what we'll do is we'll take the entire bag of redexes and do like a transpose, essentially shuffling all the redexes together, and now GPU threads will look at a totally different set of redexes than they were looking at before. This is, again, just one of the example strategies we have to unfortunately do due to the platform sort of specific architecture. One of the things we're lacking, in my opinion, is some benchmarks, but for the paper, I essentially benchmarked HVM2 with itself. Ideally, we'd also have comparisons with other platforms, but the main thing that I find interesting here is the fact that we have a single language that can run on both the CPU and on the GPU. Obviously, you get the same results, and we can immediately see that the GPU, just by nature of having more threads, will execute these computations much faster. The specifics of these operations are essentially just sorting like these large trees or lists, or summing across a tree. Of course, these computations have like a closed form. If you sum a tree of like some integers that are computed based on where it is on the tree of this size and this breadth, of course that's like a signal number, and so a compiler that knows what the value of that operation is could just return that, and that could be a program that has the same sort of semantics as this, that obviously is much faster. But the point is that we have an interaction combinator evaluator that the design is the same both for a GPU and for the CPU, and it just runs faster when it has access to more threads. Yeah, so in conclusion, there's a few things I want to mention. We're also in the process of developing like a higher level language that is meant to compile down to HVM. Here's an example like Fibonacci program, and here's the example compilation of HVM. They coincidentally fit on the same page. And we think this is an interesting sort of avenue to explore for other higher level languages, or to be transpiled to HVM, especially for like pure functions. And the primary selling point is the fact that we have this sort of hardware architecture agnostic runtime. Yeah, go ahead.
I assume in this language, like the whole point of having this new language for it is that you can tell if it's realizable and interaction, and like if the program, right?
Sorry, say that again? The whole point of...
So, you know, like 30 slides before, there was this remark that there is only a certain subset of lambda terms that can be turned into interaction.
Yes.
Yeah, so my question, or I would hope that if you have your own language, like mine will have a different language, the only reason I can see for that is if you can tell from a banned program, I mean, whether it is translatable, whether there, I think there are ways of managing that problem when you're writing a banned program, because otherwise, so what does it give you, like, yeah.
Okay, so if I understand your question, yeah, not all sort of terms in, let's say, Python or some other high-level language can immediately be encoded into this because of the reasons we talked about earlier about it not soundly evaluating all lambda calculus terms, right? There's a few avenues for this. You could have, in the case of Python, a decorator that does the syntactic checks necessary, right, for that compilation. But you're right, it's not sort of like a target for every language or for every program. Like it's not sensible to evaluate many, many terms.
But that's not my question. My question is that the problem that having your own surface language solves? Or like why do you need...
Why do we need a surface language?
Yeah, why does
Sure, that's a good question. As a proof of concept for transpiling a higher level language, right? Because we can't sort of, hello, everyone that wants like to program, please write your programs in HVM seems unreasonable to request.
You start from 4, you start from GC4, right? And then you have something that works for
Yes,
all.
Ben does have, it does a lot of transformations to make like regular, functional lambda programs work with HVM, making sure that things are linear, etc. As far as we know, there is no like specific characterization of every program that can be safely executed in this way. But we know that there are some subsets of lambda calculus terms that are.
And so is Ben like circumscribing that safe subset?
Not yet, but that's like the next step. We already know like exactly the things that we want to implement. We can have a type checker that can make sure that your term is actually some lambda.
Yeah. Okay.
So do you have a specification of a type system? What does the type system look like?
So the thing that we planning on implementing is elementary affine logic, and that's like a subset of terms that can be reduced in elementary complexity. And we know there are proofs that all of those terms are safely soundly reducing under Christopher arithmetic.
So very briefly, would you give, could you reprise, so you've given the definition of what an affine function is.
Mm-hmm.
So what's the elementary term to it?
Elementary, I mean, the affine in
So
logic.
there's only 5 minutes left, or maybe we can make the questions also.
Sure. I'll just give the very last page then, and then we'll just go right to questions. But The future stuff we want to do, like we've been mentioning, is an interaction at type system is sort of like something we haven't seen much literature on outside of polarization. Lazy mode was something that was present in HVM1, but now due to the extreme eagerness of HVM2 is no longer present, which prevents like optimal evaluation for the subset of Lambda terms we're targeting. Writing a bunch of custom runtimes is annoying if we want to change the specification, and now you have sort of 4 runtimes, 1 for C, 1 for CUDA, 1 for metal. And if you change the specification, we want to have to manage all those code bases. We're exploring the idea of sort of having a DSL that will generate these runtimes. And additionally, we want to formalize HVM's design and semantics as we don't have sort of a formal definition of HVM. That's the entire presentation, so we can go back to that question, which was about elementary affine logic.
Yeah, but actually before that, you kept referring to a paper. No, you go to the last slide because there is no link to the paper in the ICF slide. Is that the link?
Yes. It should be on the website. I'm not sure why it's not on there. I'll contact Mike about that and ask why it's not.
And also the slides.
Oh, the slides are definitely not on there because I was writing them moments ago. Yeah.
I think that is something that we might explore, but there is a general rule was that these papers are not officially published and therefore they don't want this to be publicly available.
Oh, the paper should not be publicly available? The extended abstracts as well?
Yeah, this is just for the abstract.
Oh, okay.
The papers have to be published and they have the
I see.
library, but the abstracts are not available for that reason.
I see what you mean. Okay.
So what we can do is we can ask them whether we can provide, for example, pointers to archive or something like that.
Okay, understood.
But if you go to the HVM repository, you have drafts of basically.
Yeah. I want to answer his question first, if that's okay. You had a question about elementary affine logic.
Yes. Can you give a brief summary?
So elementary like terms is a like complexity class, right? It's like the union of all exponential time hierarchies, and so that's elementary time. Elementary affine logic is a type system that you can ascribe on top of lambda calculus that's inferable, and will, like the simply typed lambda calculus, will restrict the terms that you admit. And similar to linear logic, right? It sort of it checks like linearity, but it's slightly different than just the vanilla linear logic.
You can have like some bounded amount of applications, or in their case they use.
Basically, you can statically, like you can statically.
Yeah, you can statically determine like how much of these applications. And you have
Constant bound of.
Yeah.
constant bound, and you know that they don't like interact with each other because they're kind of layered in different.
Okay.
Because linear logic alone is too restrictive, right? The linear lambda calculus is like complete. It always terminates, and so it's not Turing complete.
What about elementary convergence? I guess it's not Turing complete either.
But with the references we have, it can be, because it like defers execution. It lets self-reference. It allows for loops. You had a question. Yes.
I was going to ask, the addressing space means that you can only have 4 gigabytes of memory. Is that 4 gigabytes of memory per GPU or per concurrent HVM2 program? Like if I have a
Per program.
So I can get a 64 gigabyte graphics card and just put like 16 concurrent HVM2 programs.
But they can't communicate with each other. They,
Okay,
yeah. Correct. You said we were almost up on time. I'm not sure.
I guess we have time for one more question.
Okay.
Sorry, can I ask about the
Please.
memory encoding you had? Right, so that was informed by the limitations of the architectures you're targeting. Right, you're trying to back it into like.
Yes, that's definitely definitely an influence.
So if that wasn't the case, I'm wondering what the change would be. So like maybe the encoding of the integers with primitives.
Yes, great question.
Files.
Yeah, 100%. Yes.
Does that maybe like better performance, or is it just?
We can do many things. We can, at a minimum, increase the addressing space. Additionally, like you said, the integers right now are 24-bit. They would be 60-bit, I think, right?